Yes, thank you. And I appreciate the invitation today, and I hope you can all see my screen. I'm trusting that the top won't be blanked out, some of them in some of the slides. So today I want to look at some crop climate models and how we can use them for advisories and give a few examples. So as probably most of the people in this meeting don't really know about crop and climate models. Now I see I have a problem. You can't see the top, can you? What must
we can.
You can see it. Okay.
Yeah.
All right. So if we think about what are climate models, then they are global climate model has been used to simulate all the different factors that are affecting the Earth's climate. And it's a complex mathematical representation. It's taking into consideration the atmosphere, the land surface, the ocean, and the sea ice, and then the interactions between these. So actually the Earth is then divided into 3-dimension grid, and the size of this grid then depends on what kind of size model you are running. And so really the results are here where they do a number of mathematical, physical calculations with PV equals nRT and all those basic equations we learned in physics. And then it passes information to the adjacent cells. And so really it's about the energy balance around the Earth. And so if we think about the energy balance, we know that it's driven by solar radiation coming in, and then there's other radiation and energy transfers around the Earth. So this is how the globe would be represented. And then what is important for us is that we have downscaling of these global climate models, and we call them regional climate models, and then down to a very small local area. And mostly we looking at something like 15 kilometers square for the models that we would use. So if we look at what is happening in South Africa from this climate change point of view, we know that there's warming taking place. And over these left panels, you'll see 6 different models, and it's giving a temperature change in around 2050 of 2 to 3 degrees. And if we look in these right panels, it's up to 2100. And it is giving 3 to 5 degrees. So this is what we have to deal with in the future. And this, of course, is not only going to affect our crop production, but also affect the diseases. And so this is one of the reasons why we need to think about having some advisories that are helping us with the crop disease predictions. So if we just look at the effect of temperature on crops, this is in the temperate zone. Here's the tropical zone, and you can see for maize, there are maybe 20% decrease. If we look at the wheat production, then there can be up to 40% decrease with a temperature increase of 5 degrees. So if we're going to look at 3 degrees, maybe we would be at here around 20% decrease in the wheat production for tropical areas. Okay, so let's look at some basics also about a crop climate model. This is also some mathematical equations, and they represent the interactions then between the plant or the crop and the environment. And so it can be looked at all different levels, because we do have some different organizational levels. And so we could be looking at some cells, or we could look at single plants or the whole plant, and then even up to an agricultural region, or across the whole country, or across the whole of Africa. And so we want to look at all those different levels. So the main aim really of why people build crop models is to be able to estimate what is the harvestable or economic yield. So usually it's done via some representation of photosynthesis, and then giving how much biomass will be produced, and then using a harvest index to be able to get to some economic yield. But there are all sorts of different types of crop climate models. Some of them are empirical. They're just doing a y equals mx plus c, some kind of regression equation. But of course, these are built from data from a specific area and a specific cultivar, and so they're not easily transferable. Then there's the mechanistic models, and these mechanistic models would be explaining the behavior of the system and trying to really explain those physical and chemical and biological processes. And then, of course, we have both static and dynamic models. The static are just taking a snapshot at a certain time, and sometimes this is useful, and then we look at the different times zones. Or otherwise, if we have dynamic models, then we're usually using differential equations, so changing with time and what is happening. We also have deterministic and stochastic models. So these ones would be bringing in some of the probability of the predictions and how it may change under different circumstances. So basically, we try to simulate what is happening in that crop-climate interaction and be able to use that by putting in some different management strategies. So if we think about these simulation models, usually there would be a specific crop model for a specific crop, and it'll bring in the crop characteristics and also then bring in the environment. Most of the crop simulation models are done with a daily time step, and they're bringing in the information as standard input about what the crop characteristics are, what is the length of the growing season, and what are the growth stages and the length of those. Also, a selection of soils, and then we have a daily input of the climate data. We also have a place where we can put in the agronomic practices, so the fertilizer or the planting dates and those kind of things. Of course, to be able to use these crop models, we also need to calibrate them for the current situation, for the current cultivars, and then also to do some validation. So as somebody else earlier in the session was talking about training sets, then we would also divide our data sets so that we have some for calibration and some for validation. And mainly then we're predicting the growth. So we want to know the growth time periods, and this helps us with knowing how old the crop will be at a certain time according to the current season's weather. Also for development, so we know when flowering will be and whether it's delayed due to some extraordinary climate, and then eventually the yield and the water use of that crop. So if we think about what can we use the crop models for, firstly, we would use it for a research tool so that we can understand the system and change it and see how genetic improvements might have happened. Then we could use it as a crop system management tool, and we could also use it as a policy analysis and development of the advisories. So if we think first of the crop system management tool, then for example, here you could see that this is data from Zimbabwe for maize, and it is giving us the maize grain yield. And you can see that if we have 4 tons per hectare of mulch, and then we could look at what is the effect of 0 nitrogen applied. If we have 4 tons of mulch and we have 30 kilograms of nitrogen, or if we have a higher nitrogen applications. So we can see that here you can definitely see that there is a optimal level at a different level, different yield level for these nitrogen applications. And then also, of course, you would say that there would be a different optimum for the application of the mulch as well. So we can use this to help us to develop some advisories, balancing all of the different agronomic practices. Then we could also use it as a risk investment assessment. And this would be more for an advisory on when to have the planting date. So this is information from Bloemfontein, and it is comparing the El Nino and La Nino of the maize grain. And you can see that this is for a November planting. And here we have the La Nina and El Nino comparisons, and we can see that there's a difference between the January planting and the November planting. So we can look at how much risk we can take. So if we took here and said, okay, well, we can take 50%, then here we would only produce 2.5 tons. And if we plant in January and we go, here's the 50% risk, then we would, if we in a different season, we might only get below 2 tons. Then, of course, we can also use them for some policy analysis. And here again, we would use these type of CDF, cumulative distribution probabilities. And so here, this is again for maize in Zimbabwe. And this would be under a high rainfall agroecosystem. And this would be under medium rainfall agroecosystem. And here it is comparing the conservation agriculture against using basins or rippers or deep ripping. So you can see that under a different considerations, if we take again our 50%, we would see that at the 50% mark, here the conservation agriculture will be producing a higher yield for us. Whereas under the medium rainfall, we will see that if we take it the 50% point, then we can say that this deep ripping is going to give us the best net benefit. So this would also help us then to be able to make some kind of advisories. If we look at the climate change, then we can also see that we can look at some gap analysis. So this y-axis here is showing us the change in yield. And so if we say that we would look at some different cultivars here of Bambara groundnuts, and we can see that there is some difference in the 2 cultivars in Botswana, but in South Africa, a major difference between the 2 cultivars using that Bloemfontein data. So we can then use the long-term crop model runs for being able to do this gap analysis and selection of cultivars. But of course, there are also some gaps in our crop models. And one of them, of course, is about the modeling of diseases and pests. And part of the problem here is that there's not a holistic and powerful enough way of doing this across the whole field. And it also is not very good at simulating the pests and diseases outbreaks. So mostly what is done is that it's taken as some kind of percentage of the leaf area or something like that. And so there really is a need for some integration to be able to integrate some of the pests and disease models into the crop models. And mostly, as I said, it just does some kind of reduction in the leaf area or biomass accumulation. And of course, the variability across the field is not included, except in some of the precision agriculture applications. And this is then where there would be able to be some corrective activity. But again, it needs to have the monitoring instruments and monitoring both of the climate and also of the pests and diseases, as has also been spoken about in some of the earlier presentations. So if we think about what can the crop models actually model about diseases, then we would know that if we're going to control the diseases doing some agronomic practices, then these would be able to be included in the crop model. So if you're running the model during the season, then you would say, I have done this kind of activity as disease control. There's also a place where the chemical control for spraying and fumigation can be included. The biocontrol agents can be integrated, and then also according to the temperature. So it would either reduce or stop the reduction of the biomass accumulation, as the case may be in the crop model simulation. So if we look at what has been modeled in the diseases that could be then included into the crop models, first one is about the disease cycle and how it's infected. So if we have a theoretical increase in the disease severity, then we would be able to include that in the crop models as long as we have this trigger time and it can be brought in according to the monitoring and observations. And then this would also be then used according to the climate traits. So we would use the temperature, rainfall, many times leaf wetness, and then be able to have some retarding of the leaf growth and a decline in the biomass. And so this is one of the building blocks that has been used. And so you can see here under a number of different diseases, you would be able to show how the leaf area and the biomass would be varying according to the amount of disease infection. So if we think about some examples where we know that the diseases are affected by the climate, we've already heard a lot about the stem rusts and the other rusts. So we know that they are easily spread above 20 degrees, not so good off below 15 degrees. If we look at soybeans, then the range is between 12 and 29, so it's a very high range of temperatures, but also needs to have a period of wetness, and often with relative humidity, high relative humidity for more than 12 hours. So sometimes after some rainstorms, then this would be quite possible in the South African conditions. If we look at the downy mildew, then this has been used in the grape industry a lot, and so the hourly temperatures and rainfall and relative humidity are used, and it's divided into primary infections where the 24-hour rainfall is important, the leaves must be wet for more than 3 hours, and the average temperature should be above 10 degrees. And then, of course, the secondary infection has different environmental requirements, and so you really have to look at the details of each one of the diseases. But I'm probably talking to the converted because you guys know that. If we think about what early warning models are running right now, we know that the Grape Compass is a model that is running online, and it's a decision support system for the grape growers. And it uses the weather forecast and the climate conditions that I've already explained to be able to predict for powdery mildew, downy mildew, and botrytis. And you can see here it's made in simple robot colors so that you can see whether there's likely to be more infection or not. And it can also be illustrated on a map for the farmers in the Western Cape. Some of you might know about AgriCloud, and it was developed by the Agricultural Research Council, and it uses the weather data, but includes agricultural information, and it is tailored to the farmer specific needs and is available in 11 of the South African languages. And there is advice on the weather conditions that are conducive for spraying. So it uses some of that weather information for every 6-hour period throughout a day for the next 3 days to be able to help the farmers to make a well-informed management decision about whether they should spray or not. It's using humidity and wind and high temperatures. And so if the temperatures would be high in the middle of the day, then there would be a recommendation not to do the spraying. And so it comes with an advice for the next 3 days. So if we think about trying to formulate an advisory, Then we need certain inputs. We need some basic experimental results. And these experimental results, probably many of them are what you as scientists dealing with pests and diseases already have. And then there needs to be some relationship between the crop growth and the disease infestation and the weather parameters, so that we can then use the predicted weather, temperatures, rainfall, leaf wetness from the weather forecasts to be able to make some kind of an advisory. And of course, the satellite or drone monitoring of the fields is also useful. And then the output would be some routine advisories, so given out on a daily basis or weekly basis. And these would be location specific for a specific crop. And they would have messages that weren't just going to say it will rain, but this rain is likely to affect this or this or this. And we need to also have a delivery system in place. And that is what AgriCloud provided, was an app. And we also need to have a client database.
3 minutes, Sue.
Yes, thank you. So I'm on my last slide, so it's just exactly right. So we really need to work together across disciplines, because we do have climate models and we have weather forecasts, and mostly they down to 15 kilometers square, some of them down to 5 kilometers square. And so you can think that one farmer next to the next farmer would be getting somewhat of a different forecast if there was different weather conditions. We do have crop models for a variety of crops, and we have some effect of the environmental stress. There are some independent standing pest and disease models, but they're not well integrated with the crop models. So this is where there is a gap. And then the advisories, at the moment, there's advisories for warning about the conducive conditions for infestation. There's also advisories for spraying for pests and diseases. And there's also monitoring, which we've heard about in other talks. But we really need to be able to work together in transdisciplinary teams to be able to give the best advisories. Thank you very much.